Hi everyone. In this video we are going to go through section 3.8 titled Implicit Differentiation. So in this section we are still taking derivatives, but we're now taking derivatives of more and more relations, more and things that we can't necessarily write in typical function notation. So first a little bit about what it means for something to be implicitly defined. All right, when we say explicit, that the function is defined directly. All right, so when you talk explicit, where our equations are written as y equals or f of x equals. When you state something explicitly, you are stating it directly. All right. Then compare that to implicit. When something is implied, it is indirectly stated. So an implicitly defined expression will be one where y is contained within the equation. Now maybe I could solve that equation for y, but sometimes it gets more challenging, like here x squared plus y squared equals 25 is one that we're going to work with in this one. There, if I wanted to solve the top one for y, that would be reasonable. I could do that. If I wanted to solve the bottom one for y, in order to do that, right, we would have to subtract the x squared. So y squared equals 25 minus x squared, and then we'd have to take the square root. So y is equal to plus or minus radical 25 minus x squared. All right. Now, in order to, maybe you recognize that equation as the graph of a circle with a radius of 5. Okay. And so when I took that square root, you notice I wrote the plus and the minus. There's a poorly drawn circle. I did my best. When I took the square root, you notice I wrote the plus and the minus there. The positive square root gives me the top piece of that circle, and the negative square root gives me the negative piece of that circle. So I could, again, writing this in function notation, I could write this as a piecewise defined function. Y is equal to the positive square root of 25 minus x squared, and that is when x is between 0 and, whoops, I wrote that wrong, x is between 0 and negative 5, and then it's the negative square root of 25 minus x squared if x is between 0 and positive 5. So we can write that using standard function notation with a piecewise function, okay, and take the derivative that way, but it's in general more efficient to introduce this new technique where we take derivatives of functions that are defined implicitly. So without needing to go through the steps of solving for y and then breaking it up into pieces, I can just take the derivative of this guy directly. All right, and these are the steps for taking a derivative implicitly, for performing implicit differentiation. All right, and first we take the derivative of both sides of the equation, right? So we take the derivative. Our y is written as a function of x. It says consequently, uses a fancy word there. When we take the derivative of the sine of x, we get the cosine of x. But when we take the derivative of the sine of y, the answer is the cosine of y, but then we have this extra dy over dx term because we must use the chain rule to differentiate the sine of y with respect to x. Okay? All along so far, when we have an equation that's written as y equals some stuff, when we take the derivative of that, dy over dx, we're just writing that, or sometimes we're writing f prime of x, but when we're dealing with y's, we're just writing that dy over dx, right? But the derivative of y with respect to x is that. So when I have my y term, implicitly within the equation, anytime I differentiate a y, I get an extra term multiplying by dy over dx. We've been writing it all along. Now we've got to make sure that we write it within the equation, because we might even see more than one y inside of an equation. All right, so that's the calculus step, step 1. Then we get the algebra steps. Step 2, we rewrite the equation so that all the dy over dx terms are on the left and anything else is on the right. Then we're going to factor that dy over dx out, and solve by dividing both sides by an appropriate, by what like you've factored that dy over dx out of. Okay, and if the steps 2, 3, and 4 are a little bit confusing without seeing an example, hopefully when I go through these first two examples, it will be clearer. All right, so let's go back to that equation of a circle of radius 5. I want to find the derivative implicitly. All right, and so let's see what that looks like. I'm going to rewrite my equation. X squared plus y squared equals 25. And I'm going to look at each term individually, left-hand side and right-hand side, and take their derivatives. The derivative of x squared is 2x, just like it always has been. All right, plus the derivative of y squared. All right, we use our power rule, our regular power rule. The derivative of y squared is 2y, but when we take the derivative of a y term, as it said above, we also, by the chain rule, have this dy over dx. When I differentiate a y term, we multiply by dy over dx. Okay, that's the new thing that's happening in this section on implicit differentiation. Remember previously, below an equation that said y equals, you wrote dy over dx. Same idea going on here, just a little bit more involved. All right, then my equal sign, and then the derivative of 25 is, and always has been, 0. There we go, okay? Step 2 says to rewrite it so that any term with dy over dx is on the left-hand side, and any term, that guy over there, well, that's not a division sign, I'm just underlining it, any term that doesn't have dy over dx is on the right-hand side. So we have 2y dy over dx equals negative 2x. This problem does not involve any factoring. We can just divide to get my derivative term by itself. So here my derivative dy over dx is equal to, the 2's cancel out, negative x over y. Okay, so remember, that still represents the slope at any point. So what's kind of interesting is on that circle of radius 5, the ratio between the x-coordinate and the y-coordinate, well, the negation of that ratio at any point is the slope, negative x over y. So at any point on the circle, the ratio between the x and y coordinates gives me the slope at that point. Let's do another slightly more involved example here. Okay, this equation looks much bigger. All right, so I'm going to rewrite it first, and we're going to take the derivative implicitly. X cubed sine y plus y equals 4x plus 3. All right, so let's take a look at this first. Starting on the right-hand side maybe, right? Do I know the derivative of 3? Hopefully the answer is yes. Do I know the derivative of 4x? Hopefully the answer is yes. Do I know the derivative of y? Hopefully the answer is yes. dy over dx is what we do what we get when we differentiate that term. Okay, here, x cubed sine y. Do you see a product rule? Because I see a product rule. That's multiplication. So we're going to have to use a product rule while taking the derivative implicitly. So let's see if we can do this. Start out with my x cubed. Derivative is 3x squared. Keep the other term the same. Plus the derivative of sine y is cosine y, and then dy over dx because I'm differentiating a y term. And then that gets multiplied by x cubed. F prime g plus g prime f. All right, so that, all of that that's in green there is the derivative of that product, x cubed sine y. Then let's switch to red. So we'll say plus. Now the derivative of y is dy over dx. And then we'll go y equals sign. And then let's go with blue. The derivative of 4x is 4. I'm not going to write down the derivative of 3 is 0. All right, so there we go. There's our derivative equation. It's pretty messy. So we want to clean this up and ultimately write it as dy over dx equals. So I have a dy dx term here and here. We want to leave those two terms on the left-hand side, but this guy, I want to throw that over on the right-hand side with a negative sign. So let's see. Cosine y dy over dx, x cubed, plus dy over dx is equal to the 4 stays and the 3x squared sine y. I'm subtracting it to get it onto the other side, like that. All right. Next up is we're going to factor that derivative term from each part of this expression. So we have dy over dx, parentheses. If I take it out of the first term, I'm going to switch up my order here. I'm left with an x cubed and a cosine y. And if I take it out of the second term, there's nothing there, but I need that placeholder, so I'm left behind with a 1. And that equals 4 minus 3x squared sine of y. Last step, we divide. I'm not going to write it out, but we're going to divide by that parentheses, that factor on both sides. So my derivative, dy over dx, is equal to, the numerator is the 4 minus 3x squared sine y, and the denominator is x cubed cosine y plus 1. Okay, so again, fairly complicated, but that's how we do it. All right. So if you need another example like that, the higher degree of difficulty than the first one, please let me know, and I can shoot a quick video out showing you 1 or 2 more of the homework even. Okay. Let's go through one additional example, taking the process one step further, and we want the equation of a tangent line to that circle, x squared plus y squared equals 25, at the point 3, negative 4. Okay, so first, if we just check 3 squared plus negative 4 squared equals 25, 3 squared is 9, 4 squared is 16, add 9 and 16, and you do in fact get 25. So that's just me verifying that that point is on the line. Okay, so yay, yes, it's on the line. So what is the tangent line look like at that point? And maybe I'll even draw a little sketch here, a poorly drawn sketch. Here's going to be my 5. I'm going to draw a circle of radius 5, and there it is, right there. Again, it looks like maybe more like a football, but you get the idea. And then the point over 3. And then down 4 might be I don't have the best scale on here, but maybe right about there. And we can see that the tangent line at that point should have a positive slope and a y-intercept of negative something bigger than 5, let's say, maybe negative 6 or 7. All right, so let's see how this works out. Now, we showed earlier that the derivative at any point on that circle is negative x divided by y. So that's the slope at any point. So if I want to take my derivative evaluated at the point 3 comma negative 4, so that's just a kind of different way of writing it. So it's negative 3 over, and then the y coordinate is negative 4. So that's not terrible. Now, this was made a little bit easier because we already had the derivative. In general, you'll first have to find the derivative and then plug in your point. So this simplifies to a positive slope of 3/4. So that was what I expected to happen. The slope is positive, so it's a slope of up 3 over 4. And then if I want the whole equation of that line, well, that's where I jump to my point slope formula. Y minus the y coordinate is equal to the slope times x minus the x coordinate. So that's a y plus 4 is equal to 3/4 x minus 3 times 3 is 9/4. And then I'm going to subtract that 4. Oops. I want to subtract that 4 from both sides. So I'm going to get y equals 3/4 x minus 9/4 minus 4. And 4 is 16/4. So that's going to simplify to negative 25/4. And you should definitely check that in your calculator. I just did. So for our equation here, y equals 3/4 x minus 25 over 4. And I would be fine with those being in decimal form also. And if you check, 25 divided by 4 is equal to 6 1/4. And again, that matches up with where I expected that y-intercept to be, a little bit beyond negative 5. And that certainly is where it is. Okay, so that is the end of the video on implicit differentiation. If this wasn't enough examples for you to understand the process, please let me know. I'm happy to throw a few more out there. Like I said, I'll do one or two off of the homework in a supplemental video if anyone asks. Okay, so thank you very much for listening. Work on some homework. Let me know if you have questions, please, and have a wonderful day.